from this simple example, the moment of inertia result is dependent on the coordinate system we set up. Then the next question becomes, if we have a two coordinate systems, can we find out the connections between the moment of inertia Ix with this x versus another moment of inertia Ix if x is going to the center? And the answer is yes. And not only yes, this is a very important theorem, in fact. It's called the parallel axis theorem, allowing us to build a connection between two arbitrary moment of inertia with respect to A prime versus B prime. Let's say this is A prime axis, this is the B prime axis. Okay? So in general, we have the moment of inertia defined as y squared dA. So then, if we want to calculate this moment of inertia with respect to this A prime, okay, with respect to this. So then, what we're going to do is to write down the moment of inertia I, which is equal to y squared dA with respect to, with respect to, no, forget about it. This is A prime, A prime, this axis, okay? So the moment of, the moment of inertia with respect to A prime axis, which is defined like this. Now, if we pick up any dA point in this cross-section area, anywhere, so then this is y, which is here. Now, if I create another axis, which is called the B prime, which is passing through the centroid point this time. So this B prime is very special. It has to pass through the centroid point. This A prime can be anywhere. Can be here, can be on the top, can be very bottom, doesn't matter. So this y squared, which is the dA you can randomly identify inside the cross-section area to this axis, that's called y, which is always equal to a y prime with a distance from the same dA you pick to this new axis, B prime, plus the distance between these two parallel lines. These two lines must be parallel. So once you have this one, obviously you know the distance between these two parallel lines. So then y is equal to y prime plus d. And you have y squared, then obviously this is squared as well. Okay? We are going to expand this integrand. So this integrand should include three terms, right? One is a y prime squared, one is 2d y prime, and one is d squared. So this a plus b squared equal to a squared plus 2ab plus b squared, right? So it's going to be split into three parts. Okay? And let's evaluate each part separately. So the first part is to have y prime squared. So what is a y prime squared? Y prime squared, from the definition of moment of inertia, that is the moment of inertia with respect to B prime axis. Okay? Because if I'm asking you what is the moment of inertia with a B prime, then obviously you are looking at this distance and then square it and then do the integration. So this one, in fact, is the moment of inertia with respect to this new axis. Previously, on the left, is the moment of inertia with respect to A prime. But you expand this one, you get the first term, which is the moment of inertia with respect to B prime. Now let's look at the second term. The second term is 2d y prime. Both 2 and d are constant, right? Because when we are fixing those two parallel lines, that's d is a constant. So you can put d and 2 out of the integration. You just need to deal with integration y prime dA. That's the second term. Third term is d squared. So d squared dA. But d is constant, d squared is constant as well. So you put the d squared out of the integration, and then you just do integration dA. Now, let's evaluate these three terms. The first term, as I explained to you, this is the new moment of inertia with this new axis, we call the B prime. B prime, the moment of inertia I call I bar. That means there's a bar on top of this I. The left-hand side is still I here. So that's why I still put this I here. That's the moment of inertia with respect to this AA prime, which is equal to the first term, I bar. Second term. So in general, you just need to evaluate y prime dA with any given axis. But this axis is very special because I predefine this axis which has to go through the centroid. That's called the centroid C with this given area. If you go back to look at chapter 5, if you have axis going through this one, then what is the what is the x bar? The x bar has to be on this. And this is the axis. Then x bar equal to 0. Okay? So if the x bar equal to 0, the definition of x bar is y prime dA over A. So if that has to be 0, then this one must be equal to 0. So then the whole second term is gone. So you don't have this term if you choose B prime going through the centroid point. So this second term is gone. Now let's go to the third term. D squared is still here. What is the integration dA? Integration dA altogether is the area of this cross section. So you have this cross section. What is the area? You call A. Then that's become A times D squared. So this is the important theorem, which what we call the parallel axis theorem, allowing us to have the relationship between any moment of inertia with a given axis versus the moment of inertia with respect to a special axis passing through the centroid. So with this theorem, then you don't have to worry about many different equations to define the moment of inertia with given area. All you need to do is just to find the moment of inertia with respect to this axis passing through the centroid. And we always use I bar to represent. So once we know this one, if you want to calculate the moment of inertia with another given axis, what you need to do is just to add one term. And that term is called A times D squared. And A is very simple, which is basically the area of the cross section. And then D, or D squared, is basically the distance between the centroid axis to the axis you later choose. So all you need to do is just to find out the short distance between these two parallel lines and square it, multiply with A, which is the area of this cross section, and then you can find out the moment of inertia with given new axis. And this is a very popularly used theorem allowing us to calculate the moment of inertia with any given axis we like. So let's say if we have this theorem, we want to go back to look at this one again. At that time, just a couple minutes ago, I showed you two results, right? One is the moment of inertia with respect to this coordinate system. In other words, you have an x-axis on the bottom. And I also show you another moment of inertia, y squared dA, which is equal to 1 over 12. 1 over 12 bh cubed if I choose the axis passing through the centroid in the center like this. Now, we can use the two results we just obtained to check whether this theorem is valid or not. Of course, it has to be valid because we proved it already. But I just want to use that example to show you, in fact, that the theorem exists. So let me just quickly show you. Back to this one. So when we are talking about HB, if you have this, it's called x. So now Ix, which is y squared dA, based on this one, we already obtained 1/3 bh cubed. We integrate out by ourselves. And now if I have another parallel axis, I call it x prime, passing through the centroid of this rectangular shape. So now I have Ix prime, again with the same definition, but we did it independently, which is 1 over 12 bh cubed. If you want me to show you the result, that's exactly what we have here, right? Okay, I just did it. Now I just want to look at those two results we obtained to check whether the parallel axis exists or not. Okay? So in other words, let's say we have this one, I, with respect to this, which is equal to another one with this new axis, AD squared. I have a question mark. I want to check this one because this is what we call the parallel axis theorem, right? We just talked about. Now I want to use this example to check whether this is good or not. The left-hand side, the moment of inertia with this x-axis, we independently evaluated, which is 1/3 BH cubed. So I want to check whether this one equal to the right-hand side. The right-hand side, the first term, is the moment of inertia with respect to another axis passing through the centroid. That's called x prime. And we also independently evaluated, which is 1/12 BH cubed. Okay? Now, we want to evaluate the second term, which is called AD squared. So what is A? A is simple. That's the area of the rectangular. What is the area of the rectangular? That's a BH, right? That's the area. And then multiply D squared. What is a D squared? D is the distance between these two parallel lines. Then what's that? That's half H, correct? And then don't forget with the square. Okay? So left-hand side is still 1/3 BH cubed. But we need to check the right-hand side. So H 1/12 BH cubed. Let's reevaluate the second term. So 1/2 squared 1/4. B is still here. H, you have a square and multiply another H. That's H cubed. Okay? So now 1/12 plus 1/4. What's this? That's 1/3. Okay, because 1/4 is the 3/12, right? So 1 plus 3 is 4. 4/12 is 1/3. So finally, we can see the parallel theorem works. Okay, just with this given specific geometry. So in other words, if we are talking about a rectangular cross section, being the beam cross section, do we have to memorize all these? No, we only need to memorize one. So once we memorize one, then we can easily use the parallel axis theorem to deal with all other moment of inertias if there's a need. So typically we can memorize this one because this is somehow related with the axis passing through the centroid. And that's the unique definition. Okay? Of course, if you say, I just want to memorize this, there's really nothing wrong. You say, I want to memorize 1/3 BH cubed. There's really nothing wrong, but this is not the easiest way. Remember, if I'm asking you, how can you calculate another moment of inertia with respect to this one, which is having the distance from here to here is the 3/4. You say, okay, I'm going to use this parallel axis theorem to calculate this one. So let's say this is a moment of inertia with respect to x double prime. This one. The relationship between this and this, which is called the Ix, and this is Ix prime. The relationship between Ix double prime with Ix is not simply this, by the way. It's not. The reason it's not is the parallel axis theorem requires this one. The first term on the right-hand side must be the specific, the moment of inertia, which is respect to the axis passing through the centroid. If you want to build a relation between these two, it's not that straightforward because none of them pass through the centroid. So that's why, in fact, you better memorize this. Okay? So let's go back to look at the slide. I can show you some specific ones after people do conduct the integration. Okay, so here are some basic ones from this chart. For example, if we're again talking about a rectangular cross section, something like this, let's say the width is still b, the height is h. Now we can know if we want to talk about the moment of inertia with respect to x prime, that's through the passing through the centroid, then we know that that's a 1 over 12 b times h cubed. So this one, we just did it many times. If we need to calculate the moment of inertia with respect to y prime, that's also passing through the centroid, but with y prime, then all you need to do is just switch b to h, h to b. That should be simple enough, right? I did this as well, but the coefficient is the same thing. 1 over 12, 1 over 12, b cubed h. However, if you want to know the centroid, if you want to know the moment of inertia based on this x, then you can simply use the parallel axis theorem to get it. Or of course, if you want to memorize this again, nothing wrong, because 1 over 3, we have used it so many times as well. This is 1 over 3. Okay? I didn't talk about this, it's called J. J is called the polar moment of inertia. That is the combination of Ix and Iy. You can add them together. But this is not for the beam problem. Actually, that's later on related with a torsional problem. If you have a slender member, you give a torque, then you are going to use this J to evaluate how hard you can twist. Okay? Obviously, in addition to the rectangular, you have the triangular shape. Then what is the moment of inertia? That's a little bit more complicated. As you can see, that's over 1 over 36. If you have a circular Ix and Iy, talking about both axes passing through the centroid with a geometric center, that is 1 over 4 pi r to the 4th power. Okay? And we have a half circle. If I have a half circle, the moment of inertia with x and y are related with 1 over 8 pi r to the 4th power. If you have a quarter circle, then Ix and Iy having this x and this y, which is 1 over 6 pi r to the 4th power. And if you want to talk about ellipse, that's a little bit more complicated, but it can be also calculated using the integration two-dimensional way, because this geometry is completely described using that kind of x over a squared plus y over b squared equals 1. You can also integrate out. So these are the typical geometries, and we can find out the moment of inertia. Okay. Then the question is, do we need to memorize all this one? And in fact, we don't have to, because that's too much complicated, especially the book already gave the chart. So if I assign homework, then of course you can look at the textbook and to do whatever integration you need. If I gave you a test question, so typically I would like you to memorize this, which is called the rectangular's moment of inertia with respect to either x prime or y prime. So at least you need to memorize this one. And I believe this is the most commonly used the moment of inertia later on in other courses. So you need to memorize this one. Okay, but whether you want to memorize this or not, that doesn't matter, because as long as you know this one, you can easily derive this based on the parallel theorem. Okay, but others you don't have to memorize. So in other words, in this chapter, I think chapter 9, right? So at least you need to memorize the moment of inertia with a given rectangular shape. Okay? So next, I'm going to give you an example. But before we give you an example, let me talk about something in practice. So if you look at all the real beams, okay, they are basically not using any of these kind of shapes. Okay, real beams, not the model. Okay, when we talk about model, when somebody talk about introduce beam theory, they use a rectangular shape because that's simple, in fact, right? But in reality, people rarely use the rectangular shape beam to do the design. If you look at the buildings, look at the bridges, people rarely use these kind of simple shape beams. The reason is this. The reason is they are not very effective, even though, as I said, you have a higher H that is much better compared with the smaller H. But even that is not enough, because when we do engineering design, the most critical issue we concern is the cost. Okay, so if I can design a little bit more complex cross-section area, however, using less material and provide you with a stronger moment of inertia. That's the best we do. So that's why later on when you look at those real beams in engineering practice, basically they are using these kind of things. Okay? The reason they are using this kind of things, for example, instead of having the whole cross-section rectangular area, and they use this, it's because what? It's because this one can give you maybe 50% of the moment of inertia with this rectangular shape. But the material you are going to use, compare this one and a full bulky rectangular cross-section. They are completely different because the cost is basically proportional to the material put in. So this, you use much less material. In other words, you have a lower cost. However, the rigidity, or in terms of this moment of inertia, may be still somehow comparable with the moment of inertia of this overall rectangular shape. So that's why, in general, people would like to use this kind of cross-section area. And we understand it's a little bit more difficult to fabricate that. But even including those costs during the fabrication, in general, the final cost, which is much more better than you simply build rectangular cross-section as the beam. Okay? Then the second question becomes, how are we going to calculate the moment of inertia of this? Basically, there are two ways we can do. If you go back to look at the handbook, they basically tell you all the moment of inertia of these commonly used cross-section areas. But on the other hand, I do want you to somehow understand how to calculate just based on our simple moment of inertia of the rectangular beam. Okay? So let me first talk about this as example. And then sometime I rely on the results we got from the previous slide. And on the other hand, I can also show you, actually, I can briefly talk about this one first to give you a kind of impression before talking about this example. So let's say if we have this cross-section, and how are we going to calculate the moment of inertia with respect to x, with respect to y, for example, right? And I think one of the homework examples will be something with this, just with a different geometry. So if we want to calculate the moment of inertia with this given shape, all we need to do is use the same concept as we call superposition. And we use that superposition concept in chapter 5. So I'm switching back to my slide, overhead projector, just to show you how to calculate this, which is in fact called the wide flange. So if we have the beam with a cross-section like this, so what is the moment of inertia with respect to x, and what is the moment inertia with respect to y? Let's say x is this, and this is the y. Okay, so in fact, this is typically called wide flange. Section. Pretty much, this is the most widely used beam cross-section in real engineering. So the question is, what is Ix first? Of course, by definition, this is this. And then A is here. This is the A. Okay? So obviously, nobody can figure out if you really want to do integration just based on this. But we know there's a superposition method. So we can split this whole A into a few pieces. So now what I'm going to do, instead of having this one like this, having this is x, this is the y, I'm going to split this one into 3 parts. Because obviously the top flange is a rectangular cross-section. So this is x, this is y. So that's the first part representing this. Plus another one, that's called a stem. This is called a stem. Okay, this is the second part. And then the third part is a bottom flange here. Okay, so just to make sure the original coordinate system you set up on the left-hand side must be consistent with each components on the right-hand side. You must use the same coordinate system. That's the only requirement. And that is consistent with what we talked about in chapter 5 as well. At that time when we were trying to calculate the centroid with a little bit complex geometry at that time, right? The same thing. This whole procedure is called a superposition. Superposition method. Okay? So obviously you can make a chart or whatever you want. That's fine. But I just want to briefly tell you the moment of inertia of this Ix, it should be equal to the moment of inertia of this one first, plus the moment of inertia of this one, and then plus moment of inertia of this one. Part 1, Part 2, Part 3. So all we need to do next is to calculate these three and add them together. We got a moment of inertia on the left. Okay? So let's just do one by one. So first of all, what is the moment of inertia of this one with respect to this xy? Well, nobody knows. Because if you go back and look at the chart didn't give us this one. Right? The chart gave us the moment of inertia with respect to this axis passing through the centroid. But we have another tool which is called the parallel axis theorem. So through that theorem, we can in fact calculate this one. Okay? So that is, originally this one is the moment of inertia with respect to the centroid axis, you call x prime for example, and then plus a d squared. Okay? So all we need to do is to identify these two terms and add them together, which is the first part. Okay? So let's just briefly do it. So what is the moment of inertia with respect to the local centroid axis called x prime? 1 over 12. And then b h cubed. We just need to find out what is the b for this one, what is the h for that one, right? So what is the b for this one? This is the b. So you just need to go back to look at the original geometry. Let's call this a b. So that's going to be b times h. So this is the tiny h. Okay? I call this h here. I call h1, by the way. Let's call h1 is better. Okay? And then don't forget to add this balance term, which is called the a times d squared. So what is a? A is the area of this part, the upper flange area. That's going to be b times h1, right? Okay, so that's the area. And then times d. This time we need to identify b, the d. D is from x prime to x, this one. So this one, from the center of the centroid all the way to the global one. In other words, this is one. So this is the one you need to identify from the given picture. Let's say from here to the center of this one, let me call like a h. I already use h. Let's use m. Okay? So that's going to be m squared. Because typically they should give you this m, by the way, from the original picture. Okay? Of course, I'm not using a number. So this all together, in fact, is the moment of, let me move up a little bit, is the moment of inertia of the first part. Any questions? Yes?
Are we not including the, are we not looking at the fact that they're kind of curved?
No, you're right. Typically no. Okay. Otherwise, that's too complicated.
It's too small, so...
Yeah, you can say like that way. Yes, it's too small. In reality, if you look at those handbooks, they give you very detailed final result, which is based on maybe something curved. But there's no way you can do it analytically. Okay, so that's the approximate, but is in fact very realistic way to estimate complicated geometry, the moment of inertia. Yes, but a tiny curve, obviously, we're not going to do that. One of the reasons in reality when they build this kind of, the beam with kind of curve is because they want to minimize the stress concentration. That's a different issue. Okay, when you make something with a curve, that's you decrease the stress concentration. If you look at the airplane, all the windows are some kind of circle instead of a rectangular shape, right? Because those corners would create some kind of stress concentration. Okay, but that's a different issue. This is the same thing, in fact. It's nothing to do with the moment of inertia, but it would affect something else. So, this result, I'm not going to calculate, is the moment of inertia based on the first part. So now let's move to the second part, which is this one, the stand part. The stand part is basically plus this one. What is the moment of inertia of this one? But this one, that's easy because this axis, this x-axis, in fact, is passing through the centroid. If that's the case, that's very easy. 1 over 12 bh cubed. What is a b? This time, there's a different b, right? So this is the bs. That's called the b based on the stand part. And multiply with h cubed. The h is this, the height of this stand. So let's call hs cubed. Okay, so this is simple. This time we even do not need to use the parallel axis theorem because that axis happened to pass the centroid of the second area. Okay, number 3. The last term. What is the moment of inertia based on this one? The same thing. This time we're talking about this one. And we don't know the moment of inertia based on this one, but again, we're going to use the parallel theorem so that the moment of inertia of this is equal to I call this one x prime again, ix prime plus ad squared. Okay? Which is equal to the moment of inertia of this rectangular shape passing through the centroid is 1 over 12 again, and this is the b, and then this is the h. I use h1, right? Also h1, or it can be h2, just in case they are different. But in reality, they are the same. So h1 cubed plus the area of this flange, which is a bh1 again, and multiply with d. D is the center from the center of the x prime to this global x. In other words, this is, in fact, due to the symmetry, same m. So then bh m squared. Okay? So this is the moment of inertia for the third part. And you just add these 3 terms together, you get the moment of inertia of this overall wide flange geometry's moment of inertia. So now, let me, any questions? So let me switch back to this one. So hopefully you have an idea because they just gave you the result without giving you the detailed procedures. So finally, if we are talking about a wide flange, this is called wide flange, right? If you can see clearly, you can look at my slides later on. Wide flange shape, that's the definition, that's what they call wide flange, okay? There's some kind of tiny curve which we typically ignore, okay? So once they gave you some designation like a W18 by like a 57, for example, from these 2 numbers, W16 by 57, and then you can use the handbook to look at all the geometries about these shapes. In other words, what is the B, what is the H1, and what is from here to here. They gave you all the geometries, and then obviously you can calculate. And they calculated these moment of inertia for you directly. What are those moment of inertia? This one, Ix, right? So Ix bar means this x-axis passing through the centroid. Similarly for Y bar, Iy bar, that is the moment of inertia with respect to this one. I did not show you this one. You can think about it, because later on when I have a homework question, I would ask you to calculate both Ix and Iy. But I just want to tell you, Iy in fact is simpler than this. It's simpler than what I was showing you in fact. Okay? Because for this Iy, every 3 components is passing through the centroid. So then you even do not need to use the parallel axis theorem, in fact. Okay? But you can think about it. Later on you can do that. Okay? In the real structural engineering, sometimes they have some other shape, but the principle is all the same. For example, sometimes you have this kind of I shape. You may say, what's the difference between this I shape cross-section versus W shape, wide flange? Well, the difference in reality is not that much, except the flange here is much wider. So that's why they call it wide flange. And this I is smaller. You compare this from here to here versus here, this is much smaller than this. But overall shape the same thing. But let me tell you, this one is more effective than this when we are calculating later on so-called rigidity. Okay? Sometimes they have a C shape, or it's called channel shape. Is this channel, right? Is it channel? Yeah, it's channel, right? So it's called a C shape, something like this. If you need to calculate the moment of inertia with a C shape, how are you going to do that? Same thing. You're going to split this one into a tiny rectangle, another tiny rectangle, and another rectangle. Same thing. Okay, but the geometries can be different. The bottom line is, from this one, you should be able to calculate the moment of inertia of this one with given both x-axis or y-axis. But if you want to calculate the moment of inertia with this y-axis this time for this, then this time you do need to use the parallel axis theorem at that time. Okay? Now, sometimes we can see the angle steels. Its cross-section of the steel beam can be something like this. And how are we going to calculate the moment of inertia with respect to x and y axis? Okay? Similarly, you can just split this one into this and this. However, you think about it. The typical way we define x and y are based on the centroid of this complex geometry. If you need to calculate the moment of inertia of this one, the first thing you need to do is to go back to look at chapter 5. To go back to look at chapter 5 to identify x bar, y bar with this given geometry. And after you identify x bar, y bar, then you're going to create a new coordinate system going through x bar, y bar. In other words, this point is x bar, y bar. So that is the centroid determination based on the concept we learned in chapter 5. But the procedures are pretty straightforward, because this one, how to calculate the centroid, you just split this one into 2 parts, right? Each part is rectangular shape. And then you add them together using that kind of chart. Okay? I think next time I'm going to talk about the moment of inertia calculation based on this one. This is a little bit different from previous one, because I have something additional on top of this. So then how are we going to calculate the moment of inertia based on that?